So lecture 20, coordinate and change of basis. So hopefully at the end of this lecture, you could be able to learn how to find the coordinate matrix relative to a basis in a vector space. And we're going to move from one coordinate system to another coordinate system or change from one basis to another basis. Okay. So let me give you the theory first, and then I give you kind of the motivation example of why we need to do coordinates matrix or find coordinate matrix and change from one basis to another basis. So in the last lecture, technically in lecture 18, when we talk about basis, right? And we have one theorem that, okay, if you have a set of vectors, in this case, I call that a set B instead of the set S that we talk in lecture 18. It's just a name, right? But it's convenient for us a little bit later. So I have this set, I call set B, is collections of n of vectors. It's a basis for a vector space V. And then in that vector space, you take out one vector, and this vector is called vector V. Vector V can be expressed in as a linear combinations of all the vectors in B, and this linear combination is unique. Right? So the statement of the theorem say that the vector V can be expressed in one and only one way as linear combinations of vectors in B. I know we didn't prove this particular statement, but we have some example related to this to show that there's a unique solutions to the linear combination. Okay, so we did that. And when we find or we write vector v in terms of linear as a linear combinations of all the vectors in B, you have the coefficients, right? You need a linear combination, you need the coefficients C1, C2, C3, so on and so forth. Those coefficients in the linear combinations are the coordinates of V relative to the vector space. And that's what we're going to look for in this lecture. We're gonna look for those C's, the coefficients of linear combinations in one basis. And then later we're gonna convert or we're gonna find the change from one basis to another basis. Okay, so let's write down again the theory a little bit. So in this case, again, let B be a set of all the vectors from V1 to Vn. This is the order basis for vector space capital V. And let the vector V be a vector in the vector space such that you have this V equal to C1 times V1 plus C2 times V2 plus dot 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 up to Cn times Vn. Okay, so V in the vector space can be written as linear combinations of all the vectors in B. Now the coefficient C1, C2 up to Cn are the coordinates of V relative to the basis B. Okay. Right, so you can be able to you follow the same procedure that we did in lecture 18 and then collect all the value of the coefficients, put that in a vector or in a matrix, then you have them as the coordinates of the vector V relative to the basis B. So this, oh, sorry, the coordinate matrix or coordinate vector of V relative to B is the column matrix or column vector, whatever is convenient for you, in Rn whose components are coordinates of V. All right. So here's the notations that you may want to know to illustrate that the coordinate of a vector relative to a basis. Okay. So you have vector V. You're going to put a bracket around it. And underneath that, you have B, capital B, stand for the set of all the vectors that you use for the linear combinations. And here, this is equal to C1, C2, up to Cn. So this is the collections of all the constant or all the coefficients in the linear combinations. Okay. So that is the definitions for coordinate representations relative to a basis. So why do we need to find the coordinates matrix and then later change the basis from one basis to another basis? So I want to go back to the motivation example in lecture 18 when we talk about why we need to learn basis, right? In terms of development. Okay, so in game development, you have to understand that it's not easy to design the game with only one coordinate system. So I'm going to use the word called the local coordinate and the global coordinate, or the local coordinate in the world system or the world coordinates, right? So you have one character on the point of view of the character. And let's say you have the character standing right here. Okay. And from this point of view, you can go to this particular directions or particular locations. And it take the person go from the along the x-axis 2 units and then move up to along the y prime axis 3 units. However, that is just the point of view of the character. Now, when you design the game, you need to put the character in the entire world, right? And in the entire world, the person has a different point of view. Or technically, the gamer have a different point of view. And for that, you need the character right here will go to the same location but different point of view. Okay, now that same locations in the world coordinates has the value of 5,4. That means that particular character has to move along the x-axis 5 units and then move up by 4 units. So they're slightly different between the world coordinations and the local coordinations. Okay, so hopefully you can see that when they design the game, they not only have to design the point of view of the character, but also place that point of view or place that character in the entire scene. So it's not that simple to just create one coordinate, but rather have multiple coordinates when you have multiple characters, and multiple characters need to be placed inside the world coordinates. Okay. And because of that, you need to learn how to define basis to have unit vectors, and using unit vector as basis to define all other vectors in the vector space. And also because you have multiple character or you have multiple things inside the entire world that you are working with, therefore you need to change from one basis to another basis constantly. Okay, so I'm gonna go back to the graph a little bit in terms of this particular example that you have the coordinate matrix or the coordinate vector in of a vector x rel in are two in a two-dimensional vector space relative to a non-standard basis. So in this case, you have non-standard basis of V1 and V2, right? Now, this coordinates give you 3, comma 2. Okay, so let me illustrate something here, mention something here. So you have non-standard basis, and in this case, you have the basis to be B. Okay, so V1 is 1, comma 0, V2 is 1, comma 2. Okay. So let me write this. So the coordinate matrix of let me be careful here, of X uh, relative to B is written as follow, right? So you have the vector X and you use bracket to write the vector, and underneath that you have B. Illustrate that this is the basis I'm working with, and this is equal to 3, comma 2. 3, comma 2, or this is the column vector 3, 2. Okay. Then for any vector V can be written as a linear combination of V1 and V2. Right? So that's by definitions. Right? And for any vector V can be written as a linear combination of V1 and V2. So V is equal to 3 times 1, comma 0 plus 2 times 1, comma 2. Well, now you distribute the 3 and the 2, you have 3, comma 0 plus 2, comma 4. Add them together, you have this to be 5, comma 4. Okay. Now, from this point of view, 5, comma 4, it can be written as a linear combination of the standard basis. That is 5, comma 4 can be written as 5 times 1, comma 0 plus 4 times 0, comma 1. All right. And from here, you can obtain that the coordinates matrix relative to a new basis, that is B prime. So this prime is not the derivative in calculus, it's just another name, right? So you can substitute this with some other thing like B1 or B2 or K for that matter, right? So P prime is just the name. So the coordinate matrix relative to B prime is going to be um, B prime is equal to 5, 4. So the 5 and 4, and again, is going to be the coefficients that we have when we write the linear combination of the vector. Okay. So on one side of this picture, you have a non-standard basis. You have V1 equal to 1, comma 0 and V2 equal to 1, comma 2. A little bit of manipulations allow us to go from one basis, right, from this kind of coordinate system to this rectangular coordinate system that we are familiar with. And on the right hand side is the picture for the standard basis. And you have the basis to be B prime equal to 1, comma 0, comma 0, comma 1. All right. So that's the first example, how to get the coordinate matrix, and also you can see kind of in actions that changing from from one basis to another basis. In this case, you have the non-standard basis to a standard basis. Okay, so let's move on to the second example. You want to find the coordinate matrix of the vector x equal to -2, 1, 3 in R3 relative to the standard basis of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the three vectors in S are the standard unit vectors, right? I, j, and k. So the vector x can be written as a linear combination of the vectors in the standard basis S. So you have x is equal to -2, 1, 3. Now this particular vector can be written as a linear combination of standard unit vectors. So you can write this is -2 times 1, 0, 0 plus 1 times 0, 1, 0 plus 3 times 0, 0, 1. Okay. So the coordinate matrix of x relative to S is, so you have the vector x, put the bracket around it, then underneath that you have S, which is the basis you're working with. And in this case, the coefficients you can collect is -2, 1, 3. So that's the coordinate matrix. So therefore, you can conclude something here with this. The component of x are the same as its coordinates relative to the standard basis. Okay. All right, so we're going to continue doing some examples so that we can find the coordinate matrix or the coordinate vector where we have the value or the entries to be the coefficients of the linear combinations. Okay, so let's move on to example 3. You want to find the coordinate matrix x equal to 1, 2, -1 in R3 relative to the non-standard basis of 1, 0, 1, 0, -2, and 2, 3, -5. So you're gonna set up the so this three vectors in B. I'm gonna call this vector v1, this is vector v2, and this is vector v3. All right. So we're gonna write what we're looking for, right? So we're looking for the coordinate matrix. That is, you're looking for the entries or the coefficients of the linear combinations of x with respect to v1, v2, and v3. So first we write x as linear combinations of v1, v2, and v3. Okay, so x is equal to c1 v1 plus c2 v2 plus C3 V3. So you know the value of X, you know the value of V1, V2, and V3. Put everything in this equation. You're going to get 1, 2, -1 equal to C1 times 1, 0, 1 plus C2 times is 0, -1, 2 plus C3 times 2, 3, -5. Okay, so from here, you need to find, again, you need to find the value of C1, C2, and C3. You have this equations, vector equations. Now you can turn this into a system of linear equations. Okay, so that is we obtain, for the first equations, you get 1 equal to C1 plus 0 C2 plus 2 C3. So 1 equal to C1 plus 0 C2 plus 2 C3. Or you can rewrite this as C1 plus 0 C2 plus 2 C3 equal to 1. All right, so that's the first equation corresponding to the first component for the vectors in this equation. Okay, now for the second equation, we look at the second component. That is, you have 2 equal to 0 C1 minus C2 plus 3 C3. So 0 C1 minus C2 plus 3 C3, or you can write this as 0 C1 minus C2 plus 3 C3 equal to 2. And for the last equation, that's corresponding to the last component of the vectors. So you have -1 equal to 1C1 plus 2C2 minus 5C3, or this is C1 plus 2C2 minus 5C3 equal to -1. Then you find, again, you need to find C1, C2, and C3, and at this point we have multiple ways to do that. But the one that I'm going to use is that I'm going to turn this into an augmented matrix, run the code, and get the reduced row echelon form to find the value of C1, C2, and C3. Okay, so we turn the system to an augmented matrix. Yes. So you have the matrix of the form 1, 0, 2. Then this is 1. This is 0, -1, 3, 2. This is 1, 2, -5, -1. Okay. And we're going to use Python for this calculations, quick calculations here. So we move a second to pull up the code. So now we have a system. We can turn that into an augmented matrix. I'm going to input this information into the code. So let's say I want to modify this particular array or the particular matrix, right? So you have this is 1, 0, 2, 1. This is 0, -1, 3, 2. This one is 1, 2. -5 and -1. So you run the code and you're going to obtain a reduced row echelon form. So here's the reduced row echelon form. Indicate that you have C1 equal to 5, C2 is equal to -8, and C3 is equal to -2. So on the right hand screen, you're going to see me writing that you have a reduced row echelon form matrix. That is 1, 0, 0, 5, 0, 1, 0, -8, and 0, 0, 1, -2. So this implies that C1 is equal to 5, C2 is equal to -8, and C3 is equal to -2. All right. So in terms of coordinates matrix, so let me be careful here a little bit, or X can be written as so X equal to 5 times 1, 0, 1 plus -8 times 0, -1, 2 plus -2 times 2, 3, -5. Right? So X as a vector in R3 can be written as a linear combinations of the three vectors in the basis B. Okay. Then the coordinate matrix of X relative to B is, so you have the vector X, you're going to put a bracket around that, and underneath you have B to indicate the basis that you're working with. And this is equal to 5, -8, -2. So let's say you as the character in a game, what you do for this information, the coordinate matrix or the coordinate vector, is that you're going to go in the positive x directions 5 units and then go to the y direction in the negative directions of y 8 units, and you go in the z directions or the negative z directions 2 units. Okay, and this is the coordinate system or the local coordinate of that particular character. This is not the global coordinates. Okay, and if you want to see what this is, what this coordinate matrix in terms of the global coordinate, you have to do the change of basis later. Okay. So hopefully you get the procedure and you get, the meaning of what we obtain here. All right, so we're gonna follow this procedure a little bit and push that to do the change of basis in the vector space Rn. It's very, similar to what we have done in the past, in the couple of last three example. So the procedure demonstrated in the previous example is called a change of basis, right? That is, we are given a coordinate of a vector relative to one basis, and we're asked to find the coordinate relative to another basis. Okay, and we're going to see in example so in example 3, you have this matrix 1, 0, 2, 0, -1, 3, 1, 2, -5 times C1, C2, C3, and this is equal to 1, 2, -1. So let me go back to example 3 a little bit here. So you have that from the system of linear equations. Open this bigger. So you have a system of linear equations right here. Right? So what we're looking for in example 3 is the coordinates component of the coordinate matrix, right? You need to find C1, C2, and C3. And as I mentioned, there are multiple ways you can do that. One of the ways that turn the system into an augmented matrix, run the code, and you get the reduced row echelon form. Another way to look at this is that you can turn the system into the following system. That is, you have the coefficient matrix, multiply with all the value of c's equal to the right-hand side. Okay. The coefficient matrix, because you take a look at the value in front of the c's. You have 1C1, 0C2, 2C3. So that is 1, 0, 2. Later you have 0, -1, 3, and then 1, 2, -5. Right? So you turn the system into, so this is the coefficient matrix multiplied with all the value of c's. In this case, C1, C2, C3, and this is equal to the right-hand side of the system. Okay, so there's another name for this particular setup, which is different from what we have seen before. When you set up this matrix vector multiplications, then you take out the coefficient matrix, find the inverse, and then using the inverse to find the solution of C1, C2, and C3. But this setup is also for the change of basis from one basis to another basis. Okay. So let me note quickly that this is the matrix vector form of the system in example 3. All right. Again, there's another name for this, so bear with me here. So the coefficient matrix now has the name matrix P. For P is the transition matrix from one basis to another basis. So transition matrix from B prime to B. All right. So by conventions, what you see right here for the vector of C1, C2, and C3, or the matrix of C1, C2, and C3, is that this is X with B prime, right? So this is the coordinate matrix relative to a basis B prime. And then the right-hand side is going to be the matrix X of B. So this is the coordinate matrix relative to the basis B. So here you have X, B prime. This is coordinate matrix relative to B prime. And the last one, X, B. This is coordinate matrix relative to B. Okay. So those are the names that you need to follow. Do you have any questions for me? Good. All right. So a shorter way to write this as, or you can write this as P times X B prime equal to X sub B, like this. So you say this is change of basis from B prime to B. Now to perform a change of basis from B to B prime, we write, so to perform a change of basis from B to B prime, we write, that is, you have X sub B prime equal to B raised to -1, not raised to, but sorry, inverse of P times X sub B. Okay, so you just find the inverse of the transition matrix and multiply with this the vector or matrix to get x sub b prime. So in this case, B inverse, this one is the transition matrix from B to B prime. Okay. And of course, this is the inverse matrix of P. Okay. So you have to be careful on what basis you're working with, and therefore you carry the name. Okay. So you have P is the transition matrix from B prime to B. So P here is the transition matrix from B prime to to B. And B inverse is the transition matrix from B to B prime. Okay. I have a theorem here for the inverse of the transition matrix. We're going to go back to the procedure when we get to example. But for now, let's move on to the theorem 1, the inverse of transition matrix. If P is the transition matrix from one basis to another basis, then P is invertible, and the inverse matrix is the transition matrix from one matrix to another, right? So you start with P, which is the transition matrix from the basis B prime to the basis B. Then you find the inverse of P, which is the transition matrix from B to B prime. So if P is the transition matrix from a basis B prime to a basis B, then P is invertible and P inverse is the transition matrix from B to B prime. Okay, so it's just go back and forth between the two bases, right? If you have the transition matrix from one basis to another basis, just find the inverse of that transition matrix, and you can work backward in the basis. So I have a lemma here. I want to mention how you could be able to collect all the value of the C's, the coefficients, so that you put that in the transition matrix. Let B, capital B, be a set of V1, V2, up to Vn, and B prime is equal to U1, U2, up to Un, B2 basis for vector space capital V. And you say that if V1 is equal to C11 times U1 plus C12 times U2 plus dot 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 up to C1n times UN. Right, so V1 is the linear combinations of all the vectors in B prime. And V2 can be the same, which is can be written as linear combinations of all the vectors in B prime. So you have V, make a mistake here, sorry. C11, C12, um, So sorry, V2 is equal to C12. So bear with me. Sorry. So I'm confused. I confuse myself with the notations a little bit. So C11 times U1 plus C21. I know this is, if you notice, this is not usually what we write. CN1 times UN. Okay. But at the end of the day, everything's going to be fine. So bear with me here a little bit. So V2 is equal to C12 times U1 plus C22 times U2 plus dot 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 plus CN2 times UN. So usually what we write is that you have C11 and C12 and then C13 to the end. So C1N, right? And then in the second equation, you usually have C21, C22, C23 up to C2N, so on and so forth. But in this case, it's look a little bit different, right? But when we put all of the C's in the matrix, in the transition matrix, everything is actually in order. Okay, because you're going to take all the value in the column matrix or in the column vector and put that um in as a row, then everything is fine. So here up to Vn is equal to C1n times U1 plus C2n times U2 plus dot 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 Cnn times Un. So if these, all the vector v's or each of the vector v's can be written as a linear combinations of all the vectors in B prime, then you have that the transition matrix from B to B prime is the matrix P. So for U1, I'm gonna take all the value of C11, C12, and C1n, and then you put that in the row C11, C12, C13, C14, so on and so forth up to C1n. And then for U2, you put that in the row as follow: C21, C22, up to C2n, and then so on and so forth, CN1, CN2, and CNN. And then that's what you got for the transition matrix. All right, so let's take a quick break here. Let's take a 10-minute break, and we're gonna come back and continue with the procedure for to find the transition matrix from one basis to another basis, and then look at some examples. All right, I will see you in 10 minutes. So let B equal to V1, V2, up to Vn, and B prime equal to U1, U2, up to UN, B2 basis for Rn. And then the transition matrix, B inverse from B to B prime can be found using Gauss-Jordan elimination method. On the matrix B prime B. Okay. So technically what you have here is B prime and B like this, and you go to follow the Gauss-Jordan elimination method. And you're going to obtain inverse matrix or invert transitions, right? So you have a big vertical line here. On the left of the vertical line, you have the identity matrix, and on the right-hand side of the vertical line is going to be the inverse matrix that you're looking for. Okay. So what you're going to see is to get the inverse of P is you need to set up an augmented matrix of the form B prime and B, and then go through all the process of Gauss-Jordan eliminations method, including all the step of elementary row operations to get a different augmented matrix of this form, right? On the left-hand side of the vertical line, that's going to be the identity matrix, and on the right-hand side is the matrix that you are looking for. So what you see here is that in terms of the procedure, you need to put the new basis here. And on the right-hand side of the vertical line is then all basis. Again, you use Gauss-Jordan eliminations method or basic row operations to get identity matrix. And of course, on the right-hand side of the vertical line is the transition matrix. Okay, so that's technically the procedure. All right, so let's jump into a example here. So I have two bases as always, for the basis B and the basis B prime. The basis B is equal to U1, U2, which is 1, 0, and 0, 1. So this is the standard basis. And B prime is the non-standard basis, which consists of two vectors, 1, 1, and 2, 1. I want to find the transition matrix from B prime to B and the transition matrix from B to B prime. Right. So for problem A, transition matrix from B prime to B. All right. So from B prime to B prime is going to be the old basis in this context, and B is a new basis in this context. So new basis start here, and then you have an old basis. Okay. So the new basis is going to be this. From B to B, from B prime to B, so the new basis is here. So you're gonna have 1, 0, 0, 1. And the old basis going to be 1, 1. So you put the vector in a column, right? So vector 1, 1 put in the column, vector 2, 1 put in a column as well. Okay, so on the left-hand side of the vertical line, you have the identity matrix here. So this is the 2 by 2 identity matrix. Because by setup, if you have on the left-hand side of the vertical line is the identity matrix, then the right-hand side of the vertical line should be the transition matrix. So there's nothing for us to do there. Just we just need to draw the conclusions. In this case, this one is transition matrix from B prime to B. All right. Now part B, so that's part A, right? So the transition matrix is 1, 2, 1, 1. So let me conclude that the transition matrix is you have P equal to the matrix of the form 1, 2, 1, 1. Now for part B, you find the transition matrix P from B to B prime. So in here, you need to set up the augmented matrix of the form new basis first and then the old basis, right? So transition matrix from B to B prime. So set up new basis first and then old basis. So new basis in this case is B prime. So you have 1, 2, 1, 1. And the old basis is B. So 1, 0, 0, 1. Now you need to apply row operations or the procedure of Gauss-Jordan eliminations method to find that or to turn this matrix into an identity matrix, and whatever you're going to get on the right hand side of the vertical line is going to be the transition matrix. So I'm going to follow through with the calculations using the row operations, okay? Because in the exam, I'm going to ask something similar to this, or in the final exam, I'm going to ask something similar to this, and I'm going to ask you to perform a row operations or the Gauss-Jordan eliminations method. All right, so we have a leading one here. We need one here, and this is already a leading one, so there's nothing for us to do there. But the entry below it, all right, so this entry, you need to turn this into a 0, so need a 0 here. So to turn that into a 0, what you do is that you multiply the first row by -1, and then add with the second row to get a second row. So -1 times row 1 plus row 2 to get a new row 2. All right, so row 1 remains the same. Row 2 is this, right? So -1 times 1 is -1. You add it with 1, you get 0. Now -1 times 2, you get -2. Add with 1, you get -1. And then -1 times 1 is -1. Add with 0 is still -1. And -1 times 0 is 0 plus 1 is 1. So now you have the second row of the form 0, -1, -1, and 1. Okay. So what you need, so you're done with the first row, right? You have the leading one, the entry below that is 0. Now you move to the second row and you need to have the leading one for the second row. So you need 0 here. Sorry, you need 1 here. So need 1 here. So how could you turn that into a 1? Very simple. You multiply both sides by -1 or divide or multiply by, sorry, multiply both sides or multiply the second row by -1. So I get distracted with this. Okay, so multiply the second row by -1. It's -1 times row 2 to get the new row 2. Right, so you're not gonna have any change for the first row. And this is 0, 1, 1, -1. Okay. So that one is a leading one. Therefore, the entry of both that has to be a 0. So I have need 0 here. So to get the 0 there, what you do is that you multiply row 2 by -2, add with row 1 to create a new row 1. So row 2 remains the same. And row 1 is going to be, so -2 times 0, add with 1, you still have 1 here. -2 times 1 is -2, add with 2, give you 0. And -2 times 1, add with 1 is -1. And -2 times -1 is +2, add with 0, you still have +2. Okay. Now, you're basically done, right? Because on the left-hand side of the vertical line, you have an identity matrix. This is a 2 by 2 identity matrix. And therefore, on the right-hand side of the vertical line, that is the transition matrix from B to B prime in this case. So transition matrix. Right. Then you can conclude that the transition matrix from B to B prime is the matrix of the form -1, 2, 1, -1. Okay, so that's one example on how to find the transition matrix from one basis to another basis. And the bases we have here are in two-dimensional vector space. Now we're going to move on to a different example on a two different non-standard bases, right? So in example 4, you have basis B is the basis with a standard basis, right? And B prime is the non-standard basis. Now in example 5, you have both bases to be non-standard basis. And you're going to go through the same procedure as before to obtain the transition matrix. That is, you set up an augmented matrix where you have a new basis first, and then the old basis, apply the row operations to reduce that into identity matrix and transition matrix. Okay. So there's two parts to this. I'm gonna do part A, very similar procedure to example 4. But part B, I'm going to use the code to help me with the calculations. Okay. Give me 1 second here. So 102, 100. Then row 2 remains the same as well. 0, -1, 3, 0, 1, 0. Now for the last row, what's going to happen is you have -1 times 1 is -1, add with 1, you get 0. Then -1 times 0 is 0, add with 2, you get 2. Then -1 times 2 is -2, plus -5 is -7. Then -1 times 1 is -1. -1 adds with 0, you have -1. Then -1 times 0 is 0, add with 0 is still 0. And -1 times 0 is 0, plus 1 is 1. Okay. So you're done with the first row. You're done with the leading one in the first row. The entries below that should be 0. Now you move on to the second row. You need to you need to find the leading one, right, for the second row. So you need 1 here. So to turn that into a 1, you multiplied second row by -1. So you have this is -1 times R2 to get a new R2. First row and third row remains the same. So 1, 0, 2 remains the same. 1, 0, 0. This is 0 to -7, -1, 0, 1. Now for the second row, you multiply by -1, so you get 0. This is +1, -3, and this is -1. 1, -3, 0, -1, 0. Okay, so you have the leading one in the second row already. So the entry above that should be 0. The entry below that should be 0 as well. So we need a 0 here. So to turn that into a 0, you get to do, so I'm going to use row 2 here. So -2 times row 2 plus row 3 to create a new row 3. Row 1 remains the same. Row 2 remains the same. All right, for row 3. -2 times 0. Right. Add with is 0, add with 0 is still 0. Then -2 times 1 is -2. Add with 2 becomes 0. Then you have -2 times -3 is +6. Plus -7 is -1. Then you do -1, -2 times 0 is 0. Add with -1 is -1. Then -2 times -1 is +2. Add with 0 is +2. Then the last entry, -2 times 0 is 0. Add with 1 is +1. So you're done with the second row. You have the leading one, the entry above and below that are zeros. Now for the last entry, what you do is that you're going to turn this into a 1 to get the leading one. All right, so to do that, you multiply that third row by -1. So -1 times row 3 to get a new row 3. So row 1 and row 2 remains the same. So 1, 0, 2, 1, 0, 0, 0, 1, -3, 0, -1, 0. And row 3 is going to be 0, 0, 1, 1, -2, -1. All right. So you have the leading one in the third row. The entries above that should be zeros. Right? So you need the zero here, and you also need the zero here. So I'm going to take care of one row at a time or one number at a time. Okay. So to get to turn this into a zero, what you need to do is that you multiply +3 with row 3 and with row 2 to get a new row 2. Okay. And to get a 0 here, what you need to do is you multiply row 3 by -2 and with row 1 to create a new row 1. Okay. And you follow the same procedures that we had before. And if we do the calculations correctly, you should get this should be 1 0 0. This is 0 1 0. This is 0 0 1. And the entry on the right hand side, so row 3 remains the same, 1, -2, -1. Row 2 should be 3, -7, -3. So let me do the quick calculations here. So 3 times 1 is 3, and with -3 is 0. So this is the 0. Then 3 times 1 is 3, and with 0 is 3. So that's why you get +3. Then 3 times -2 is -6, and with -1 give you -7. And 3 times -1 is -3 with 0, and with 0 is -3. So that's what you got for the second row. Now for the first row, just going to give you the answer here, -1 or 2. Now you're done, right? So this is the reduced row echelon form. On the left-hand side is the 3 by 3 identity matrix. And therefore, on the right-hand side of the vertical line is the transition matrix from basis B prime to the basis B. So this is the 3 by 3 identity matrix, and this is the transitions matrix. So you can conclude that the transition matrix from B to B prime is equal to the matrix of the form -1 4 2 3 -7 -3 then 1 -2 -1. Okay. So let's, instead of doing this by hand, let's enter the information of the augmented into the code to see if we get the correct answer or not, or we get a similar answer. All right. So let me modify this code. The first entry should be 1 0 2, then 1 0 0. The second row should be 0 -1 3 0 1 0. And the last row should be 1 2 -5 0 0 1. Okay, now compare the result you get from the computer, from the code, with the results that we get doing this by hand. So yes, so the right-hand side of the left-hand side of the vertical line is the 3 by 3 identity matrix. And the right-hand side of the vertical line should be -1 4 2, 3 -7 -3, and then 1 -2 -1. So that's the transition matrix. So that's it for me for lecture 20. So again, in this lecture, we talk about change of basis. You move from one basis to another basis. And when you look at the basis, you look at also look at the coordinate matrix, so the coordinate vector. Okay, so that's it for me. Let's take a quick break. We're gonna go back and we're gonna do lecture 21, which on the eigenvalues and eigenvector.